Okay, classically, if we wanted to calculate how long it would take for a particular muon to get from the upper atmosphere where it was produced to sea level, the Earth's surface where it would be detected, then that that travel time, delta t, remember this is just classical calculation, no relativity, is just the distance traveled, okay, which is 15 kilometers, divided by the speed, which is again very close to the speed of light. So we'll just approximate that with the speed of light. That'll be an estimate. And so this is 5 times 10 to the minus 5 seconds, or 50 microseconds. If we compare that with the muon lifetime, okay, which is about 2.2 microseconds, then we get, so let's 50 microseconds divided by about 2 microseconds, and so the ratio is about 25. And this is, again, this is the ratio of the travel time, the classical travel time to the muon lifetime. Now, if so what this says is that the time that it would take for a muon to get down to the Earth's surface from where it was created in the upper atmosphere is about 25 times longer than the lifetime. Okay, and so this it should be obvious that this implies that there should be very few muons left to measure. So particularly if you make a differential measurement, you measure the flux high up and then you measure the flux very low down, and you take the ratio of those two things, that ratio, the ratio of the number of the flux at the sea level to the flux at high altitude should be very, very small. Okay, so there should be very few muons left at low altitude. Okay, and that's what Rossi and Hall sort of, I guess, were expecting. The fact that they didn't get that is evidence of special relativity, as we'll discuss now. Let me show a kind of a diagram of the situation from the classical point of view first, before we move on to the relativistic stuff. Okay, so just to make the previous discussion clear, here's sort of a kind of a schematic picture of the classical prediction. The muon is produced up here in the upper atmosphere. It only goes this far. It goes a very small distance relative to the 15 kilometers that it needs to go to get to the ground and be detected. Even though it travels at very close to the speed of light, in only 2 microseconds it only goes that far. Okay, and so that's basically the anomalous. That's why the flux, the large flux that they measured on the ground, was anomalous. Now let's basically look at two different relativistic explanations to the muon experiment, and these two different explanations are relevant in two different frames of reference. Okay, so to set this up, what we're going to imagine is that we have two observers, Bob and Anna. Bob is an earthbound observer. Okay, so Bob is standing here down on the ground. Anna is an observer that's traveling on a rocket, and that rocket is moving alongside the muon at the same velocity. Okay, so it should be clear from that description that Anna is in the rest frame of the muon, and Anna also has a clock on board the rocket, so she can observe the time in the muon's rest frame, and Bob can observe Anna's clock, and we know from time dilation that that's going to be a different rate of time.